We were talking about our syringe problem. The end of class on Friday. What did we actually decide to do with this company's syringes?
We decided that this was like a outlier almost, and that they still make good syringes, still buy from them.
So we decided that this variation was not unusual enough to reject the idea that we would buy syringes from them. So we kept our null hypothesis, we chose not to reject. Okay. When we did that, we used the normal distribution. Now, we were told in the problem that 99.7% of the syringes needed to be good. We found 14 defective ones. I used the normal distribution. We had an assumption that these were normal. How can I check whether or not the normal distribution is the right one to use? If you go back and look on Friday, we even decided what would the types of errors be. We talked about whether or not the p-value was the right thing. What is the condition that allows us to decide whether or not we can use normal distribution? Sandra?
Maybe the amount of times that we do the experiment.
Well, we're only using the experiment, doing the experiment once, so I got one shipment, and I'm testing this one shipment of 3,500 syringes. So unfortunately, that if I were doing the experiment a whole lot, then I would expect my sampling distribution to become normal as I do it more and more. But I'm using the distribution as normal to try and test this one sample. It was something specific about a proportion in particular that allowed us to decide normal versus not normal. Leo, you had your hand up as well.
So is it like something like greater than the 0.05, then we did this test too?
Well, but that is what allows me to decide whether or not to accept or reject our sensitivity, alpha, which in this case was that 0.05?
I think we find out the probability is like 0.137.
Right, and our alpha was 0.05. And we got a p-value of 0.1397, which is bigger than that, so we don't reject our null hypothesis. But that tells us about this test. And that's still saying I used the normal distribution to get that p-value. Am I allowed to use the normal distribution? Because that's the assumption we made when we did this whole problem. Go back to the confidence interval section from last chapter. In chapter 8, when we talked about a confidence interval for our proportion, we said we were going to use Z. when something occurred. What's that something? On page 293 in chapter 8, we have this comment dealing with proportions. It says the statistic may be assumed normally distributed when the sample is large, right? And then directly underneath that, it gives me what it considers to be large enough. As long as I have 10 in each group. At least 10 successes and at least 10 failures. Now we had 3,500 needles. If this had been a good sample, then I would have 3.3% of those as our value. So the answer to this question is it depends on X and N minus X. If we had had this proportion right here out of 3,500 syringes, what is 0.997 times 3,500? What is 0.003 times 3,500? If both of those numbers are bigger than 10, then this is sufficient. And in this case, 0.003 times 3,500 is bigger than 10. And this one is definitely bigger than 10, isn't it? Question. Now, if we go off of the sample, our X is 14. Alessandro?
If it wasn't like bigger than 10, we should use the t-student.
I need to figure out which way the distribution should go at that point. I could say what I need is a bigger sample. Right? Because if I had, or a bigger proportion, 99.7 is going to be too hard to find. So, yes, I could use a t-distribution. But then, think about this t-value with 3,500 degrees of freedom. Right? That's a really big number of elements. That's going to be really close to the z-distribution anyway. So I run into a problem of how to rectify this. There are more options rather than just using the t-distribution. Although I think using the t-distribution would be helpful, I'm not sure it's the best idea here. let me jump forward to the edge. If I don't have a normal distribution, what should I do? Oh, wait a second. I just thought about these as two categories, right? Passing and failing. What's the last experiment we did, the last type of distribution we did that talked about passing and failing? Or successes and failures? There's a name. There's a distribution. There's a table. Well, I got two cases. Prefix means two. Everybody gets to fail Latin at this point. There are two wheels on a bicycle. Bi, right? What's the thing we did here in this class that starts with bi?
Binomial.
Binomial. Successes and failures. So what I could do instead of using the t distribution is I could say, let's do a binomial distribution and ask if what I'm really thinking about is a 0.003 chance of failure and a 0.997 chance of success, what is the probability that I get out of 3,500? I get 14 more than 14 bad needles. And then I could look at this chance and I could say, is that actually, I think I want to go the other way. Let's not use more than. Let's use less than 14. Think about the binomial picture, right? The binomial picture has each individual bar. My tables. So really what I'm looking for is I'm looking for the number down here. Problem is we're doing this out of 3,500 tests, right? This is where the numbers get ugly, right? Because I want what is the chance that I had no failures plus the chance I had one failure all the way up to the chance I had 14 failures. And each of those requires me to say out of 3,500, combination of that many, this is the number of failures, so 0.003 to the 0, 0.997 to the 3,500, and that's just for the 0. And I'm going to have to do that 15 times. Isn't that atrocious? This is a binomial approximation to our distribution. And whether it's a t distribution or a z distribution, I can use this if I don't know whether or not it's normal. I can think of my proportion as my chance of failure and success. Now, because I'm raising these numbers that are smaller than one of these giant powers, these are going to get to be really small numbers. This is, at this point, I would plug this into a computer. I wouldn't do this by hand. But you see how I can take a normal-ish or a t-distribution looking thing and say, I don't actually know if it's normal or not. Let's replace it with our binomial. Because that picture really does kind of look like this one. It's just discrete instead of continuous. Now, this is a non-simple problem. But I like it because that's an exact probability. That's a fixed count. Instead of doing z-calc and z-crit, this calculates p directly. And that means I go right to the p-value, and that's easier to do. Questions? A small p-value means I should reject my null hypothesis. I'm more likely to reject it based on the alpha. If alpha is 0.01, maybe I won't reject, depending on how small p is. But that's the point, is that my probability is calculated to be in that rejection region that we're talking about, regardless of whether left or right or two-tailed. In that two-tailed test, split the area in half, right? That means those critical values got further out. The chance has to be smaller to reject here. In a sense, two-tailed tests are stronger tests than a single-tailed test. That's why we were using the alpha over 2 for confidence interval, because we had the two sides. It was really a two-tailed test. And that means that if we think about our numbers, if alpha is 0.05, then z of 0.025 is further to the right than z of 0.05. If there's 5% of the area above this line and only 2.5% of the area above this line, that line has to be further to the right. If I reject because I'm in this 0.025 region, I'm definitely going to reject because that part is contained in this part. If I only had one tail. This means that when you are looking for stronger results, doing a two-tailed test is going to give you a stronger setup. But if alpha is smaller, that means fewer type 1 errors, fewer false positives, but it increases the likelihood of a false negative. So there's a balance between those two. We have to work carefully to ensure that we have balanced our error possibilities. Question. This is why we will see the default assumption is almost always a two-tailed test because it's a stronger test. Problem number 51. To encourage telephone efficiency, a catalog call center issues a guideline. At least half of all telephone orders should be completed within 2 minutes. Subsequently, a random sample of 64 telephone orders shows that 24 calls lasted 2 minutes or less. That's what I wanted. Does the sample show that fewer than half of the calls are completed within 2 minutes? So, the new guideline says you should be doing at least half your calls in under 2 minutes. I need a null hypothesis here. If I am doing the policy the way they say I should, what proportion of my calls should be finished in the appropriate amount of time?
Can I say like the norm could be 2 minutes or less, maybe.
Null is not about time. Null is about number of calls, not number, proportion of calls, because I'm thinking about a proportion instead. So rather than think of the time, think of what amount of calls.
24.
That's how many came out in this sample. That's not the null hypothesis. The null hypothesis is based on the standard we want to be held to, my benchmark. The benchmark up there says at least half. So my benchmark is 0.5. I want at least half the calls in 2 minutes or less. See how the benchmark's about the proportion of calls? I want the proportion of calls to be at least half. 0.5. At least means bigger than or equal to a one-tailed test. So what's my alternate hypothesis?
Maybe pi less than a half.
I'm not living up to it. Now I can say, let's look at our actual sample. In our sample, of 64 calls, we found 24 of them were completed in 2 minutes or less. Those are successes. They actually tell me in the text, assuming alpha is 0.05. So I'm going to write that down over here so that I have it for later. If I were being successful, half of 64 is
32.
32. There would be 32 in the success pile, 32 in the fail pile. I can use a normal distribution. Both of those numbers are bigger than 10. So I can use Z. I don't have to do this binomial bullcrap. I can use Z. All right, let's try it. I need a calculated Z value for my proportion. Okay. I take my proportion, subtract the benchmark, divide by the standard error. Standard error. For a proportion, that's benchmark .50, and then 1 minus the benchmark over n, all under a square root. Please notice that the top of that fraction is 0.5 times 0.5. That's 0.5 squared. The bottom of the fraction, inside the square root, bottom of the fraction is 64, which is 8 squared. So I take the square root, I get 0.5 over 8. When I divide here, 0.5 over 8. 525 0625. Hey, that works out really. This is rigged really nicely, isn't it? This works out to be -2. So I can ask right now, at alpha being 0.05, should I say, yes, we're doing okay, or no, we aren't? Should I keep, support, or reject my null hypothesis? There are 2 ways to do that from here.
We can look at Z-grid.
I need the critical, right? So, Z crit. Hey, wait, Z crit is 0.05. The Z that goes with 0.05. This is in one of 3 places. It is either on the formula sheet you are writing for this exam, or it's in your table, because you can use your Z table to look this up, or it's on your calculator, because this is the inverse normal. We're doing a one-tailed test by putting 0.05. So, what is my critical Z value this time?
3196.
That would be correct if we were doing a 2-tail. Because if I go back and I look at 1.96, 1.96. The area above 1.96 is 0.025. We want the area to be 0.05. So instead of 4750, I want 0.45, right? Or 0.95 if you're using table C2. You'll notice there's the 975 that goes with 1.96, but I want 0.95. When I look back, that's up here.
We get 1.645.
Bang, bang, bang. It's between 1.604, 1.64 and 1.65. That's 1645. That's our halfway mark. However, that's the number. Am I doing a left or a right tail? Go back and look at our alternate hypothesis. Right. The alternate hypothesis? That's to the left of 1/2, isn't it? If that's to the left, then we're doing a left tail. I don't want 1.645. I want negative 1.645. Or I can use absolute values. Is this number outside this one in a left tail? Negative 1.645, and then my z value is -2. We are in the rejection zone. Absolute value of z calc is larger than the absolute value of z crit. I reject. What's the other way I could have come up with that sentence? With the p-value. What is the p-value? 2. -2. Right? That's our z that we calculated right there. So p is the probability that z is less than -2. What is the chance that z is less than -2? That comes right off my binomial distribution table. -2.00. Chance of being less than that is 0.0228. Why does that tell me I should reject? Jacob? Oh, okay. Alessandro?
We reject when the value is like less than the
And alpha here is 0.05. This is smaller, we reject. Now, what does rejecting the null hypothesis mean in this problem? This is the storytelling part of data analysis, which is what statistics is. I did this sample of calls. I got this number. So what? You have to now go tell your bosses at this catalog company, hey, this is what's happening with the call center. What's happening with the call center? I'll put the scenario back up.
It says that, we don't have top of the telephone orders, within 2 minutes.
We did not meet our goal. So we need to do something about this. Now, you could recommend a number of things. You could recommend training for the phone operators, but we are not meeting the goal you set. Give us more money so we can have a training session on how to get through the catalog orders faster. Maybe we need to teach these people not to be such chatty people on the phone. Maybe we need to automate this system and use more web portal behavior so it's faster to do all of this. We could replace operator here, by the way, with the computer algorithm. You call on the phone to make an order, you speak to their AI. The AI is too damn slow. How do we make it more efficient? This doesn't have to be people. This could be the navigation of the phone tree in the first place. There are too many steps. It takes too long to get to the actual ordering portion. But now you can say the answer to the question, no, we are not meeting the goal you set. How do I fix that? The last question up there. Is the difference important as opposed to just statistically significant? Does this matter? We wanted half of our calls to be done in 2 minutes or less. What was our percentage for this sample? Say again?
5%.
Why 5%? Oh, wait a minute. Give me the reasoning you're picking the number.
I was looking at alpha.
Alpha is our confidence level, our sensitivity for our test. Unfortunately, it's not the percentage of what we saw in our sample.
0.375.
The 37.5%, that's our sample value. That's what we saw when we went and looked at our group of 64 calls. We wanted it to be 50%, we're at 37.5%. That is clearly statistically significant. It's an unusual z-value. But is it practically important? If I tell you you need 50% and you come back and say, here's 37.5%, you'll be happy with that. So there's an actual substantial difference here. These two numbers are not just far apart in terms of their z-score, they're far apart in practical effect. You tell me 50% of my calls should be done in 2 minutes, and I do only 3/4 of that, 0.375. I tell you you're getting a 75%, that's a C. That's not a great thing in this situation. Now, I don't know how big this call center is. Maybe this is, I don't know, Mary Kay Cosmetics, and they sell billions of dollars of product a year. I need them to be moving product, right? Maybe this is Joe's Crab Shack down the road and they sell $200 a week and it's not that big a deal. So this is now where the story comes back into play. Does this matter? We know it's statistically important, but is it practically important? Questions? You'll notice that I did not need a z-crit if I instead directly calculated the p-value from the z-value I found. I just need to know which direction my test goes to calculate that p-value appropriately. Talk to me. Either it's Monday and your brains are still in bed from the weekend, or it's before lunch and you're just suffering from hunger pangs and going, oh. Talk to me. There are some additional types of calculations we can do on our proportion, on our sample size. There's things called power curves, which connect this idea to the CDF instead of the PDF. So we look at variability in a different fashion. But I think that's a little more detail than I want to cover at this level. So here's a question to ponder. We did this because of this policy. I want half the calls answered. What if instead of establishing a benchmark, I said, I want you all to improve call response. I want the average call time to go down. You'll notice average call time is nowhere to be found in this problem. But I could say to you what I want is for the call times to get faster. How could I do something like this? To figure out, remember I said we were going to train the operators. We were going to improve their speed, teach them not to be quite so chatty on the phone, decrease the phone tree, speed up the AI interactions. However we were going to do it, we're going to make this faster. So you give me budget and I go spend that money on training my operators. Here's a 3-hour seminar on how to be faster on the phone and how to be faster in the system. The orders will get faster. Did it work? How can I tell? That's a more general question. You go out, you're doing training. Did it work? Or did you basically waste 3 hours of my time sitting there where I could have been pushing pencils? How do I know?
You can repeat the experiment.
I have to repeat the experiment. And I have to do a test comparing the people before to the people after, right? So that's a different setup because these tests that we have been doing here test a single sample. What happens when I don't have one sample, but I have two? I just talked about it before and after. I could just as easily talk about exam performance for this class versus my other statistics class. Did I get better at teaching this course than I was last semester? I need to know how you guys are doing versus how my course last semester did, or a year ago, right? I have more populations to look at. How can I test what's going on? How can I figure out how to do this for two groups instead of one? Because everything we're doing here compares my group to my benchmark. That's what I'm going to start with on Wednesday. And that's the start of chapter 10. Two important things. That means chapter 9 is finished. That means your homework for chapter 9 is due on Friday. Chapter 10 is the last of the 3 chapters on hypothesis testing and confidence intervals that is the subject of exam 3. That's chapters 8, 9, and 10. The review sheet for that is up. Start now, because I'm pretty sure that's only 2 weeks away. Today. Exactly. 2 weeks and a day. I will see you all for 1/4.